In the third part of the lesson 4, we present two other important cycles, the Stirling cycle and the organic Rankine cycle. The Stirling cycle is a cycle for a closed volume of gas with external heating, external cooling and regeneration. We represent the cycle in the diagram PV. The first transformation is the isothermal expansion 1-2. The position 1 is also displayed in the picture with the corresponding position of the piston and the shaft. The isochoric cooling 2-3, the position 2 is also displayed in the picture. The isothermal compression 3-4, the isochoric heating 4-1. In the very ideal case, the isochoric transformations are exchanging the same heat that is fully recovered within the cycle via a regenerator. The regenerator is this exchanger in between the two pistons. Also in the picture aside are represented the cycle phases of a real engine in the alpha configuration, where the pistons are having a crank angle of 90 degrees and are in separate cylinders. One cycle corresponds to one revolution. As a reference machine, we use the Mod 2nd automotive Stirling engine developed by NESA. In the video comments, we will add also the corresponding link. The working gas is pressurized hydrogen. The thermal efficiency, the maximum, 38.5%. The power output, 83.5 HP, corresponding to 62.3 kilowatt. The mean operating pressure, 27 megapascal. The maximum and minimum temperatures, 1093 and 343 Kelvin, respectively. The engine configuration is the alpha type Stirling engine, and the motor configuration is a 4-cylinder V-block, single crankshaft and double acting. The maximum motor speed is 4000 RPM. In the first model, we consider an ideal gas and full regeneration. For the gas hydrogen, R is 4125, Cp 14,438 Joule over kilogram per Kelvin. And for the time, we consider the unitary mass because we have no further information. We assume a range of plus minus 60% between the mean pressure and the minimum and maximum pressure. We say P1 the maximum pressure and P3 the minimum pressure. P1 is then the mean pressure into 1 plus 60%. At this pressure corresponds the maximum temperature T1, and by using the ideal gas state equation, we find the specific volume of the state 1, 103.6 liter per kilogram. The minimum pressure P3 is the mean pressure into 1 minus 60%, and the temperature is the minimum temperature T3, and the specific volume we calculate with the same formula as above, considering now the different values of temperature and pressure, and we land to 131 liter per kilogram. This is the maximum specific volume and this is the minimum specific volume. P2 and P4 we calculate with the state equation as well. Let's find now the work and the heat of every transformation. The thermodynamic work over the transformation 1-2 is, as we have already discovered in the previous lessons, the product of the mass, the constant R, the temperature, which is the same between the states 1 and 2 because isothermal, and the logarithm of the pressure ratio. We find 1025 kJ. The work and the heat are equal for the isothermal transformations. The work over the transformation 2-3 is 0 because isochoric. The heat is the product of the mass the specific heat at constant volume and the temperature difference, we find negative 7,735 kJ. The work over the transformation 3-4 is still isothermal, so we can use the formula seen above, finding negative 332 kJ, and this is also equal to the heat. The work of the transformation 4-1 is 0 because isochoric, and the heat is the product of the mass Cv and the differential temperature. But because the temperatures are the same, just opposite, this is practically opposite to the heat of the transformation 2-3, also 7,735 kJ. If 100% of regeneration, then heat 4-1 is 0, because this heat is fully recovered by the heat of the transformation 2-3 by means of internal heat exchange. The thermodynamic efficiency is, for definition, the ratio between the thermodynamic work and the given heat, that is Q12 plus Q41, but because, as told, Q41 is 0, it remains only Q12, and then we find 1025 minus 332 for the work over 1025 for the heat, that is 67.6%, and we recognize that this is the efficiency of the Carnot cycle. Practically, the Stirling cycle with the complete regeneration has the same efficiency of the Carnot cycle, that is the maximum possible efficiency across the given minimum and maximum temperatures. We repeat now the calculation with a perfect gas and using only 90% of regeneration, which is more realistic. In this case, we get the values for work and heat by the tool Thermonator. The result is here aside in the table, and we find, considering also 90% of regeneration, 38.7%, which is very close to the efficiency declared by the vendor of the machine. Work and power we cannot assess now because lack of information. Actually, we do not know the size of the motor, and so we cannot estimate the exact mass of the gas contained inside of the machine. The organic ranking cycle is adopted for a closed volume of vapor in a saturation region with external heating, external cooling, and possible regeneration. We represent the cycle in the diagram TS. The first transformation is the compression 1-2, and it is in the liquid region. Then we have the isobaric heating 2-3. The first part from 2 to 2 seconds is sensible heating. Then we have 2', 3' latent heating, and then 3', 3 superheated. The transformation C, the adiabatic expansion 3-4, and finally the isobaric cooling 4-1. In the picture are represented the cycle phases without regeneration and a simplified process schematic. The evaporator and condensers are heat exchangers run by fluids external to the cycle, typically water. The choice of the cycle's fluid is crucial to secure good performance in the selected temperature ranges. As a reference, we consider an organic ranking cycle for a geothermal power plant. In the video comment, we put a link to this reference. The working fluid is N-pentane, the mass flow rate 20 kg per second, the net power output 962.9 kW, the lower operating pressure 150 kPa, the higher operating pressure 1000 kPa, the maximum temperature 139.6 degrees, the expander adiabatic efficiency is 80%, and the thermal efficiency of the cycle is 9.5%. In the first model, we use real gas and reversible transformations. We assume the expansion 3-4 being isentropic. In the second model, we use still a real gas, but the transformation 3-4 is irreversible, is not isentropic any longer. And in both cases, we consider the flow rate being 20 kg per second. Below the chart is also represented a schematic of the process with the corresponding steps. The cycle process is represented in both diagrams TS and PH. The transformation A is the isentropic expansion 3-4. The transformation B is the isobaric cooling 4-5. The transformation C is an isentropic compression 5-6. The transformation D is an isobaric heating 6-3. The number of the steps are not corresponding to the one seen in slide 34. The intermediate process states are also represented by the states 54, where the pressure is the same of the states 4 and 5, and the steam quality is 100%. There is only vapor. The state 36 has the same pressure of the states 6 and 3, and the steam quality is 0%. There is only liquid. We observe that the fluid is a vapor, as we said in the beginning. Therefore, within the saturation region, there are two phases, liquid and gas. The saturation region is displayed in the bell within the charts. Let's find the technical work of the cycle. The technical work is the sum of the works along the transformation 3-4 and along the transformation 5-6, and it is a product of the mass flow and the differential enthalpies of the two transformations. Altogether, we find negative 1520.1 kW. The heat given to the system is Q63, that is the product of the mass flow and the differential enthalpy. We find 10,122 kW. All the values we can get from the table aside. The thermodynamic efficiency of the cycle is the ratio between negative technical work and the given heat. We find 15%. Let's see the irreversible case. Here we replace the expansion 3-4 with an adiabatic irreversible transformation using the expander efficiency, which is given, and this is 80%. If we display the ratio of the enthalpies of the points 3, 4 and 4 prime, and we solve for H4 prime, we find 617.3 kJ per kilogram. And then we can find the technical work of the cycle. The new work is the sum of the work over transformation 3-4 prime and the work over transformation 5-6. The last one is not changing. The result says negative 1210.1 kW. If we assume the mechanical efficiency of the gearbox being 92% and the electrical efficiency of the generator being 95%, we can determine the useful power L star as a product of L prime, eta M and eta E. Altogether, we find 1057 kW, which is not far from the datasheet value of 962.9 kW. The useful efficiency is the ratio between negative useful power and the given heat. We find 10.4%, which is closer to the datasheet value with respect to the previous model. Thank you for your attendance. I hope you have enjoyed this video. See you in the next videos. Bye bye.